Okay, hello. Today we are going to start chapter 5 about binomial distribution. So, this chapter is quite different from the first four chapters. So, the first four chapters are more about like fundamentals, more and more like it's about how to describe and how to summarize data. It did not require any assumptions, or it's just more about calculation. How you like whenever you have a random variable, then there is an expectation, there is a probability distribution. But today, we are going to take a different approach. Like so, in general, let's think about natural science or science in general. In science is kind of is how to explain. It's about explaining the world, like what you see, and to explain the observations. Science use models, and a scientific model can be explained as a simplification of phenomena or observations using assumptions. Like in economics, in physics, like biology, like whatever natural sciences, social sciences, they have their models, and the models are a simplification of phenomena, and it provides a framework to understand what you observe, right? That's science. And in statistics, also there are statistical models. And today, we are going to learn the simplest possible statistical model. So, what we're going to do is the distribution may look very complicated, but actually, under several assumptions, we may be able to simplify the distribution a lot. Or, that means, under certain assumptions, you may describe a seemingly complicated distribution with a small number of parameters. That's what we are going to do in this chapter and in the following chapter. So, as I said, the probability, it's a big difference. So we are going to use the concept of probability and the mean and the variance that we learned in the first four chapters. But but the difference is the assumptions. So the expectation exists for any numerical variables, but um, like if you add additional assumptions, then it can simplify the distribution much better. So in chapters 5 and 6, we are going to learn two statistical models, two probability distribution models. One is the binomial distribution model, and the other is the normal distribution model. So, and of course, there are many more models, and but all of course, all of them are important, but I'm not going to introduce all of them. So, if you are interested, you may look up the textbook. Here, the textbook chapters are given this way. So the keyword is binomial distribution. Okay, let me start with a brain teaser question. So I will show you 5 random experiments, and among these, one random event is different from the others. Let's think about what's different. A. Outcome from a coin toss. B. Gender of a randomly chosen person. C. Whether a randomly chosen student has a passing grade in calculus or not. D. Price of a randomly chosen dish on a restaurant menu. And E. Answer to a true-false question. So all of these 5 examples are a kind of random outcomes. And one of them is of different nature. What's that? Guess it? And there is no single right answer. like people may have different ideas about this question, but what I wanted to choose is this one. So price can be any number, right? Like $1, $2, but the others, like say outcome from a coin toss is heads or tails. Gender is male or female. And has a passing grade in calculus is pass or fail, or pass, yes or no. And answer to a true false question is true or false. So the other 4 examples are kind of yes or no questions. They are binary outcomes. That's a big difference. But the price of a dish cannot be binary. It's like, as I said, $1, $2, $3. Any number is a possible outcome. So this is what we are going to study here. This is the first assumption we are going to make. And if we, this is the simplest possible random variable. And that from here we are going to build a statistical model. So we will define a binary random variable as a variable that has only 2 possible outcomes. It can be yes or no, man, woman, like true, false, win, lose, positive, negative. You can think about a lot of examples of binary random variables. But in general, generically, we are going to call 2 outcomes as success and failure. Success and failure, I'm going to call them success and failure. But by the way, even if I call them success and failure, it doesn't mean success is good and failure is bad. It's just sometimes, like so man and woman, for example, then like if you call man as success, that's also fine. And if you call woman as success, that's also fine. It's just generic, labeling. So it's value neutral. Success is not good. Failure is not bad. So don't be confused. And it's like encoding. I'm going to encode success as 1 and failure as 0. Because earlier in chapter 3, we learned we need to have a numerical variable to define an expectation and the variance. So we are going to encode a binary outcome as 1 or 0. It's like digital, right? And 1 will be referred to as success, 0 as failure, right? So that's just terminology. And so our random variable takes this form, x equals to 1 or 0, right? So this is under that assumption. This is the assumption basic structure. And if you know that x is a binary random variable, then there are only 2 probabilities, x equals to 1 or x equals to 0. If you know these 2 probabilities, you know everything, right? That's a simplification. And if you simplify it further, because if you know one probability of 1 is p, then automatically the other probability must be 1 minus p, right? If the probability of yes is, let's say, 80%, that means probability of no is 20%. So they are just flip side of a coin. So if you know one probability, then the other probability is easily inferred. Therefore, in the end, we just need one parameter to describe the entire probability distribution. Because we assumed that the random variable is binary. So you may think it's obvious, but yes, it's obvious, it's trivial, but from here we are going to develop more complicated results in this video, like in the following videos. So wait a little bit, wait a few more minutes, then you will see actually it's not that simple. Okay, so this is the full probability distribution. P is a number, probability. So 1 equals, the probability for 1 is P, and 0, 1 minus P. I'm going to use this notation throughout this chapter. So P is always probability of 1. So, right, so far, we made two assumptions. X is a binary random variable taking 1 or 0, and probability of 1 is P. So these are two simple assumptions, and then we define the random variable X as a binary or Bernoulli distribution with parameter P. This P is the parameter for this distribution, because if you know this parameter, you know everything about the distribution. This is the simplest possible probability model. By the way, Bernoulli is a statistician, legendary statistician, like several centuries ago, and he defined this model, and so we call this distribution as binary distribution or Bernoulli distribution. And we denote this in like this. So a random variable X and wiggle, this wiggle sign means follows. X follows binary distribution with parameter P, or equivalently Bernoulli distribution with parameter P, right? So the wiggle sign means follows. A random variable follows a certain probability distribution. Okay, this is a brief introduction to binary distribution. So, as I said, this is just an example of probability model. But in general, what you can see from that example is that if a random variable or random experiment satisfies some assumptions, then we may be able to make up some parameters that can fully characterize all the distribution. So, like even if there are two possible outcomes, we only need one parameter. It's a simplification. And like if you add more assumptions, then the simplification will be more powerful. And parametric distribution family, sometimes you may hear parametric distribution family means, so it's a set of all the possible distributions satisfying the same assumptions. Like for example, binary distribution P includes any distribution with P equals to, say, like 1%, 2%, 3%. So depending on, like, if you vary P, then it can make up a lot of distributions. And of course, the shape of the distribution will be different. If you collection of all of those distributions is called parametric distribution family. They share the same assumptions and the same parameters, but the value of the parameter may differ. But all the possible shape of the distributions is included in here. And examples include Poisson distribution, exponential distribution, gamma distribution. So if you study like statistics more, then like at some point you will encounter them, right? Sooner or later, if you take another course, I believe you will see them, but I'm not going to cover them in this course. So but the idea is like we make assumptions, and so we extract the information as parameters, and then that's a simplification. Okay, so in the next video, I'm going to start a coin flip example, and we will study the properties of the binary distribution. See you in the next one.